Okay, welcome to Module 23 on sampling and bootstrapping in Python. So here's just sort of a motivating story back to hospital wait times. So a hospital reports that the average emergency wait time is 42 minutes. But then we, as knowledgeable data scientists, might have several follow-up questions, including, how much could this number of 42 minutes have changed if different patients showed up that particular day as opposed to the ones we did observe? Is this week clearly worse than last week? Maybe it's clearly better than last week. And are there any policy changes, any interventions to workflow in this emergency room that could help or could hinder the wait time, or is it just noise? So our goal in this module is to build some simulation and resampling tools in Python that can help us reason about any kind of effects that can be the result of sampling or intervention or just timing. And we'll construct interval estimates to say, well, the average is 42 minutes, but we have this range that we're dealing with. So in this module, you should be able to explain the difference between a population, a sample, and a sampling distribution. You should be able to simulate sampling variation for simple statistics. You should be able to implement a basic bootstrap procedure, which we'll define. You should be able to construct and interpret a bootstrap confidence interval. And you should be able to diagnose when a bootstrap-style method is reasonable. So let's just get our scaffold in place. So here's some key concepts. The population is the full set of all of the units you care about. So this could be all of the emergency room visits in a particular year. So it could be a population of an entire nation or an entire world. It could be that you're not measuring anything to do with individual people, but instead you're dealing with transactions at a bank that you work at. The population just basically means absolutely every possible source of data. Whereas a sample is just a subset that you actually observe. So maybe when you're doing an analysis of a population, you only have a subset of Canadians who live on the peninsula of Halifax. Maybe if you're looking at bank transactions, you only have a small sample of transactions made in a 6-month time period under review. Or again, if you work at an emergency room, maybe you only have the 120 visits sampled, filtered from last week. And then a statistic is a number we compute from the sample. So a sample mean wait time, a sample proportion of patients seen within 30 minutes. It's just like a measure applied on the sample. So the sampling distribution of a statistic is a distribution. It's like a histogram that we would see if we would repeat the entire sampling process many times. So why do we care about sampling distributions in particular? Why even make the distinction? There are a couple of questions we like to ask. So for example, if the true average wait time were 40 minutes, how extreme is our 48-minute observation, right? So there's a true data generating process behind the scenes. If we were to observe absolutely every member of the population, the wait time should be 40 minutes, but we happen to sample something that's 48 minutes. Is that extreme? Is it not extreme? If it is extreme, how extreme is it? Those are the kind of questions we'd like to ask and answer. If there's a difference of 3 percentage points on a click-through rate, is this meaningful or just noise? In a previous module, we had this set up where you had an email campaign and you tried to get people to click through on your website. A difference of 3 percentage points, is it meaningful or is it not meaningful? This is a question that we'll keep coming back to, but it's an important one. The question not about the 3 percentage points on click-through, but the fundamental question of how can you tell if a particular measured difference is meaningful or not on any experiment. And then how wide would your plus or minus interval be around a point estimate, right? If you talk about the average being 48 minutes, would you expect 46 minutes to 50 minutes to still be a reasonable estimate of an interval, or is that too small, or is it too big, and so on? Without some model of sampling variation, a claim like the average is 42 minutes is incomplete. What we always want is to further qualify and quantify those kinds of statements. So something a little bit better would be the average is 42 minutes, and the typical sampling variation is around plus or minus 5 minutes. So here's the example of bootstrapping in one picture. Instead of just repeatedly sampling new data from the population, which would be impossible in practice. Like instead of, we have a certain amount of data that we've collected, and at great expense or at great difficulty, and there's just no way that we're going to be able to get more data. So we'd like to be able to keep on sampling things on an ongoing basis, but that's just not reasonable in a lot of contexts. So rather, what we can do is repeatedly resample with replacement whatever data we actually have in the first place. And what that looks like is something like this. We have observations of wait times. Each of these blue points represents a patient who came into the emergency room, and across all of these patients we have a sample mean of 40.1 minutes. And imagine if this particular sample here is only some 10% of all of the available data that we collected over the past several months. We get a particular mean for this sample, a particular sample mean, which is 40.1. But if we were to then put that data back, shuffle the data, and get another 10% of all of the available data, so from that 10% sample, we compute another sample mean, and then store it, put the data back, shuffle it, take another 10%, compute the sample mean. You get the idea. You would get a distribution over bootstrapped means. So this histogram in red over here represents the count of all of the different means we might get. We've binned them, obviously, into little buckets. And you can see there's a sort of a Gaussian normal-looking bell-shaped curve over here, which describes all of the means. Given a distribution like this, and given like a sorting we can do, we can go back to the idea of percentiles and quantiles, and we can compute where the 2.5 percentile is and where the 97.5 percentile is, right, indicated here by these black bars. And what that tells us is that everything between these two is the 95% of the data, right? So 97.5% of the data falls on before this black line on the right. 2.5% of the data falls before this black dashed line on the left. Therefore, everything in between is 95% of the data. Right? So this is sort of 95% of the time, the wait time will be somewhere between 38 minutes and 42 minutes, it looks like. Down here at the bottom is just a couple of different samples. Here's 3 samples. So this is, the blue dots represent wait times for one sample. We get one mean. Another sample will yield a slightly other mean, 39.9, 39.3, and so on. So we've done this dozens and dozens of times to get this distribution. So this is sort of a stand-in. It's a simulation, so we kind of imagine that different 10% of people came in to the waiting room. This sort of helps us estimate an earlier question we had on a previous slide, and it's sort of a stand-in for the true sampling distribution. So we can be reasonably sure of our expectation because we've resampled so many times. There are, of course, challenges to this approach, but that will be left as an exercise to you. So yet again, a little anti-example. We want to avoid treating one sample as the pure truth, right? So if a manager who doesn't know anything about data science says, well, we measured 50 patients, among them the average wait time was 37.6 minutes, therefore from now on we're just going to say that the true average is 37.6. This is, one of the most superficial approaches to data science a person can take. So, there's randomness on who showed up that particular day, right? There's all this noise that exists in the real world. The sample size is very small, so 50 patients, that can be a large number in some contexts, but in the context of waiting rooms, this is a small sample size, so it doesn't really give you a decent enough spread or an estimate of what the data ought to look like on a typical day. And then there's selection bias. So maybe that day had a staffing issue, maybe there's a snowstorm that we tend to get across Canada that just changed the behavior on that particular day, and if we just sampled the next day, we'd get a very different distribution. So you can come up with a lot of these on your own. So the takeaway here is using a single sample statistic, as if it's a precise claim of truth, instead of couching it in all these claims of uncertainty and statistics of uncertainty. That's superficial, and we don't want to be superficial. We want to try to seek out the truth and indicate whenever we can when we don't have it. So bootstrapping and sampling simulations help us visualize and quantify the uncertainty, as we just saw a moment ago with this distribution. So we have a sampled mean over this bootstrapping process, and we have like bounds on our estimates about our confidence about where the estimates might lie. So going a little bit deeper now, let's just get our terms straight again. So we have now x sub 1 all the way to x sub n. These are the wait times for n patients we have in a large data set. Therefore, our sample mean, x bar, is just the typical equation that defines our average. So we just sum up over all of the wait times and divide by the total number of wait times. That gives us our sample mean. Occasionally, and in previous modules, we use the Greek symbol mu to indicate the average of something. And usually mu is meant to mean the average of like the true distribution. And often we don't use it that way. We use mu sometimes to refer to the sample distribution, but more technically and more pedantically, more correctly, using x or using the variable with a bar on top of it to make it clear that we're talking about just the mean of this sample and not the true mean of the world is one way to just make sure that we're dealing with our terms correctly. So in theory, this sampling distribution ought to be centered around the true mean mu that I just mentioned. So there's a real average wait time mu, there's the one we sample, and the two of them should be close to each other, and when we produce sample means, they should be somewhere around the true mean. The spread of these sample means that we're computing, we can think of as standard error, and it will shrink in a way similar to 1 over root n. This may be a bit of a stretch, so we can move on, but this is just for your knowledge. Because we don't actually know the population distribution, we only have a certain sample for a particular day, and because we're deriving formulas for every new statistic, this might not be realistic. The idea of bootstrapping is to just approximate the sampling distribution of x by resampling our data in the way that we showed on a previous slide with that graph. There is, for those interested, there's a formal treatment of the probability of statistics behind this, so go ahead and read this free book for more mathematics for machine learning if you're so inclined. The algorithm for bootstrapping for a mean is fairly simple. We have our samples, x sub 1 to x sub n. We compute our initial original statistic, like I mentioned a moment ago. Now I'm using lowercase x, but this corresponds to uppercase x from a few slides ago. And we have this computed statistic theta hat, which is our estimated sample mean. So for B, like standing for bootstrap, from the first iteration all the way to big B might be something on the order of 2,000. We can draw a bootstrap sample of size n, whatever n was, with replacement from our sample. Actually, this is a bit of a mistake. This should be, we can choose a sample of size n from some larger data set, x sub 1 to x sub m, some larger sample. And we'll compute a statistic on this sample. Okay, so we initially had our initial statistic, which is just theta hat, but we'll run this big B times, and every iteration will get a slightly different mean x bar. We take all of these computed statistics, in this case just our means, x bar, and this will help us estimate our standard error, which is a sample standard deviation of this collection of statistics. Again, in this case, just computed x bars. And then this will allow us to compute what we call confidence intervals using percentiles. Again, I even used the word confidence deliberately a few moments ago, but if we take the 2.5th percentile and the 97.5th percentile, then as by definition, 95% of the data should fall between those two bounds. And then we can say with 95% confidence that the estimate should lie between these bounds because of our bootstrapping experiments. So the same kind of pattern will work for various other kinds of statistics. So here, our statistic theta was the mean, but we could have taken the median from our sample distribution. We could have taken proportions if we have labels. We could have taken differences between their observations. Any kind of statistic you can compute on a sample of data. You can compute for each of the subsamples we take, each of these big B times. And then over those big B collections of statistics, you can compute standard error, confidence intervals, and so on. Just going a little bit more in detail, this is optional for those who don't care, but for all of you who do, just going in a little bit more detail. Bootstrapping in this way, so sampling with replacement and computing statistics on every sample, i.e. bootstrapping, works best when the observations are independent and identically distributed, so performing the shuffling and performing the random samples will make sense. And when the statistic is what we call a smooth function of the distribution, when it can compute it in a way similar to what we saw with just the sum over observations, like the mean from the previous slide. If these conditions hold, in particular, the bootstrap distribution will converge to the true sampling distribution as the size n grows. If your sample is bigger and bigger, then the averages you compute on that sample ought to be more and more similar to the true world statistic mu in the case of averages. And the more bootstraps you perform, the bigger the value of big B. I mentioned 2,000 on the previous slide, but this can get bigger and bigger. The more of these resampling you do, in theory, the closer your computed statistics should be to the truth, right? So it should make intuitive sense. The more data you're using to compute your sample means, the closer those sample means should be to the truth because your samples are bigger. And the more and more of these bootstrapping procedures you do, the more iterations you do, when you compute your overall statistics, when you compute the average of the average, that average of the average should be closer to the true mean. You can kind of see this again, just going back a moment on this distribution. So any one of these observations can be somewhat far from the true average, but if you look at the distribution over all of these sample averages, the average of the average being somewhat just slightly above 40 ought to be relatively close to the truth. So in some more advanced courses, you might see some proofs or some definitions that as you increase n, towards infinity, if you have that kind of time, you'll see sort of proofs about the rate of convergence. How quickly does your average of average approach the true average? So rates of convergent results is something that is a bit of a stretch, but can be important when you're doing machine learning, when you want to know how many iterations you have to do of a procedure. And then there's other variants. There's a parametric bootstrap and there's block bootstrap for data in which the IID, independent and identically distributed assumption doesn't hold. There's different versions of what we're talking about here that are a bit more advanced, but obviously that's a discussion for some other time. So for this course, we're just treating bootstrapping as this practical simulation tool and focus on when it's appropriate to use it and how to interpret it at a very high level. But again, it's always good to go deeper. And there's this classic treatment of it from 1994 by Efron and Tib Shirani. So you can check that out at this link. So just some quick examples. Here's our synthetic ER wait time data. We're going to just have 120 emergency room visits, and we're going to have two levels of triage. There's going to be urgent, people who need to be seen urgently. They're going to have shorter wait times, and then the non-urgent subset of individuals who come to the ER might have longer wait times. So again, as usual, here's some code which you can download from the slides to help obtain this data. And here's just a sample of the head of this data frame. So we have one patient. They're viewed as being urgent. Their wait time is 28.3-ish minutes. Someone who's non-urgent or flagged as being non-urgent might have to wait 35.6-ish minutes. So we can go ahead and inspect this sample. So again, describe and passing to the describe function include everything. We'll give you output like this. How many measurements do we have? It's 120. How many different types do we have of triage? There's only two, urgent and non-urgent. What is the more common one? It's non-urgent, and so on. You can't really compute the mean, standard deviations, or minimums of this nominal category, urgent and non-urgent, but you can compute these statistics on our wait times. So you can see here the mean is 40.8-ish, the standard deviation is 12.8-ish, the minimum wait time was 16-ish minutes, and so on. So one thing I want you to just consider and to jot down here is to think about the typical wait times, so means and medians. You should be able to find the median in this table down here. If you're having difficulty remembering which of these statistics is the median, I'd recommend going back to the discussion on statistics. But you can compare mean and median and think about it a little bit. Think about the spread. So the spread here is described both in terms of the standard deviation and to a large extent between the minimums and maximums. Think about the count of observations. What do all these tell you about these computed statistics, just at a high level? Should be pretty quick. Here is just a graph showing the wait time distribution in little buckets. Over 120 samples, we have the number of patients in each of these buckets, and you can see visually what the distribution is. It looks to be a monomodal distribution with one big hump, and the average here seems to be around 40 minutes, which we've observed before. So let's compute the mean wait time and the some other statistics using bootstrapping. So here the number of bootstrapping is going to be 2,000. This is the big B from a few slides ago. And then for, I don't care about the variable. I'm just iterating over each of these bootstrapping iterations here. So for nothing in that range, just take a random sample from the wait times with replacement and compute the mean, and then add, so here's the sample mean from that sample, append it to an ever-growing list of boot means, which initially is the empty list, but for each of my iterations, I'm just going to keep on adding the sample mean to that list of boot means. Now I have I'll take that data frame, I'll convert it to a NumPy array and store it in and restore it in the variable called boot means. So a moment ago, boot means was a list. Now it's a data frame. So I can take the actual mean from the 120 samples I have, and I can take the percentile differences from all of my samples between 2.5 percentile and 97.5 percentile. This gives me a confidence interval of the low end of my observations and the high end of the observations, between which it falls 95% of my samples. And I can just report everything here. So I have the original mean, which is 40.8-ish, and then I have the confidence interval that goes between 38.5 and 43 minutes. Okay, so the first number is the sample mean, and the interval at the bottom here is the bootstrapping percentile, confidence interval of 95%. Here's just visualizing everything. So this is just a visualization of what we saw a moment ago. The average here is shown in blue, and then the 2.5th percentile and the 97.5th percentile are shown with these black dash marks over here with the values we just computed a moment ago. And you can kind of see visually, this should make sense to you. It looks like about 95% of the data falls between these bounds. So we got our best guess for the average wait time. This was stored in ORIG mean a few moments ago. And we have this plausible range given the sampling variation that goes between confidence interval low and confidence interval high minutes. So, if the hospital claims we keep the average wait time under 35 minutes, does this look defensible from this graph? I mean, I'll leave this to you as an exercise, but hopefully that should be pretty clear and obvious to you. So now, again, we're bubbling up from data science, and we're using our analysis of the data to make decisions about our context, our use case, which in this case is hospital wait times. So assume now that the policy is not 35 minutes, but the policy is that we are meant to have an average wait time of at most 40 minutes. And then we have a bootstrapping, and our confidence interval falls between the values L and U. If the upper end of the confidence interval is less than 40 minutes, that ought to be good evidence that we're meeting our target, right? So if 95% of the time, or if 97.5 percentile is less than 40 minutes, that's pretty good. That's a pretty good estimate that we're hitting the target of 40 minutes or less. If the low end is bigger than 40 minutes, which is to say if only 2.5% of the observations are less than 40 minutes, or less than whatever L is, and L is greater than 40 minutes, this is pretty strong evidence that we're not meeting the target, right? The low end of our confidence interval is bigger than our minimum policy of 40 minutes. That means that wait times are much bigger than our policy target, and therefore we're doing a very bad job of meeting the target. If the confidence interval, if L is below 40 and U is above 40, so our policy of trying to hit 40 minutes or less is somewhere between that confidence interval, then this is somewhat ambiguous now, right? This can either mean that we need more data, we need to keep on sampling data to see how well we're doing. It might mean that we need different targets or metrics. Maybe we should focus on the 90th percentile weight, right? Like, so looking at all of our distribution of all of our samples, finding something at the higher end. Does the person who weights more than 90% of all of the observed people, do they wait more than 40 minutes? Maybe that's the metric we should be looking for, and not averages or confidence intervals. Maybe we need to rethink things if looking at the confidence interval is ambiguous. The point of this is that computing bootstrapping and computing lots of observations over multiple samples gives us a range of estimates as to where we expect a statistic to lie. And then we can compare those statistics against our target. Sometimes it's going to be obvious that we're hitting the target or not, if the distribution is either entirely to one side or the other of the target. But if the confidence interval overlaps where the target is, we need to rethink how we're approaching the problem. And then in this case, we ought to rethink different targets or metrics, which again just hammers home this idea from this course generally that if you want to be a data scientist, you can't just have one tool at your disposal. You have to have multiple tools you can apply to a problem. So bootstrapping doesn't magically solve anything or prove anything. It just sort of helps us to quantify or measure our uncertainty or our range of uncertainty to help us make better decisions, which again is the whole point of doing data science. Here's another example. Here we're back to doing website sign-up experiments. So you and I, we work at a company, we're on the website team, we have an old landing page, and we have a new landing page, and we want to see if there's any difference between these two in terms of click-through rates. The outcome we care about is whether or not there's a conversion. So if a user went to our website and they signed up to our newsletter or to our service, whatever that is, we get a positive one classification label, otherwise we get 0. So once again, here's some simulated data. We have, in this case, it's nicely balanced. We have 200 observations of the old website, 200 observations of the new website, and we have variance. So person 0 uses the old website and they don't convert, they don't sign up. The next observation also uses the old website and they don't convert. The next observation uses the old data set and they don't convert. This is only the first 5 data sets over here, so it's pretty dull, but you can look at the entire data frame, AB, and see what you come up with. This is called AB, by the way, because we're doing A/B testing. A is the old website, B is the new website, and we're just comparing these two things equivalently side by side, which is what we call A/B testing. So we have our conversion rates. Again, we talked a lot about group by recently, so I'm not going to get into it again, but we're performing some aggregations. Those aggregations are mean, sum, and count. I mentioned in class the other day that one thing you can do is to take this list that you pass to the aggregation function and try using different possible functions. So we're using mean before, now we're using mean, sums, and counts. And just, all I'm doing in this code is asking to be shown the results of these. We have now the kind of click-through rates of people who use the new website and the old. So 26 people convert use our service on the new website. Only 18 convert or use our service on the old website. Amongst 200 observations in each of these cases, that translates to 13% and 9% respectively. So we have some statistics. So it looks like, again, people who don't take this class and are extremely superficial or don't know how to think in terms of data science, they might look at 26 and 18, and if they're really clever, they might realize that 26 is bigger than 18, and they'll think that the new website must be better because the number is bigger, therefore the new website must be better at converting people than the old one. But this is a relatively small sample potentially. Is the difference between 26 and 18 actually meaningful or not? We need to dig a little bit deeper to consider this problem. So very quickly, p hat old is the conversion rate of the old page. That's 9%. P hat new is the conversion rate for the new page. That's 13%. And delta hat is just the difference between these two, right? So a 4% difference. This is just computing it down here. But as we can see from this table, we have this 4% difference, which is delta. I'll mention just for a moment here, like the difference between 13% and 9% is exactly 4%. In class, we briefly talked a little bit about numerical instability. And then that's kind of what's happening here with this 1 over here. What's going on with 1? We can maybe talk about this at some other point. It's something you can ignore for the moment because of how small this 1 is. But occasionally when you look at very small numbers in Python, there's numerical instability that happens in just the representations of the numbers in RAM. And you end up getting this kind of weird behavior where 1 pops out where 1 might assume there to be a 0. Again, is this 4% difference, just noise? Is it just randomness? Is it like a random accident of how we've sampled the data? Or does this represent like a true superiority of the new page over the old page? So we can use bootstrapping to try to investigate this problem. We can bootstrap. We can sample rows within the combined data set of the old page and the new page. We'll use replacement. So we'll sample some of the data. We'll put it back. We'll essentially shuffle, sample another 10%, and do this over and over again, and then compute conversion rates between these. So now big B is 4,000. So we're going to take 4,000 random samples, which might overlap with each other, compute averages for those samples, compute the differences between the old pages and the new pages, and store them. So you can go through this yourself. Here is the loop over these 4,000 bootstrapping iterations. Here we're computing the means of individuals using the old page. In this sample, those using the new page. So the variant is new. And we care about those who converted. What is the mean? We store that in mean new. We look at the difference. So I want to see if there's any improvement from using the new page versus the old page. So you can just subtract those two. This gives me my diffs, which I called a delta before in math mode. And then I'll just keep on adding these differences to my ever-growing list called boot diffs. Once that's done, I can compute the percentiles. I get this from the NumPy package. The percentiles are computed on the boot diffs list I computed a moment ago. I get the 2.5th percentile, the 97.5th percentile. This gives me my 95% confidence interval in the low end and the high end. And then I can just print everything up. So that is down here. So my confidence interval. So like over these 4,000 iterations, I compute the difference in conversion rates on the new page versus the old page. I store it, and I look at the statistics over that entire sample. And as you can see and you can run this yourself, and again, you're highly advised to do so. On the low end, actually sometimes the old page does better, and we get a negative delta, a negative difference. So I am, 2.5% of the time, the difference is 2.3 percent. People prefer the old page over the new one, which is why it's negative. And on the high end, so 97.5% of the time, there's a up to a 10% difference. So the 97.5 percentile is 10%. Click-through rate is better on the new page than the old page. Here's a visualization. For those of you who like visualizations, through all of our 4,000 samples, we've gotten differences between click-through rates or conversion rates on the new site versus the old site. This gives us our distribution, which is another nice normal Gaussian-looking distribution. The average is over here in blue, which you can barely see. We have our low end of the 95% confidence interval down here, which is negative. We have the high end, which is about 10%. So this is the like over multiple samples comparing the new page versus the old page. This is what we get, and like no difference is this red line over here. So generally there seems to be an improvement of the old page. So the overall skew, or the overall I guess tilt of this distribution is somewhat positive. So most of the time through all of these iterations of the bootstrapping procedure, there's a positive difference between conversion rates on the new page versus the old page. So it looks like statistically the new page is better. But for the particular observation we took a moment ago, where we only saw a 4% improvement, in click-through rate, this falls between the confidence interval of minus, I think it was 2.3% up to 10%. So is this particular sample, does it actually seem to indicate any superiority? 4% might not be necessarily enough evidence by itself to suggest that the new page is better than the old page. So, to interpret this, if the confidence interval barely crosses the 0 line, this might indicate, a weak evidence of improvement. Actually, so just riffing on what I mentioned a moment ago, not only is not only is a 4% improvement in click-through rates or conversion rates on the new site compared to the old site, maybe not enough evidence to suggest that the new page is better. Actually, even the no difference at all, so the 0 delta, is within our confidence interval, right? So 95% of the time, our difference between the new page and the old page will be between this region. Somewhere between the upper and lower limits is no difference at all, which is sort of indicating that there might be a little bit of hesitation about claiming that the new page is definitely better than the old one, right? A still substantial amount of the time, given all of our 4,000 samples, the old page actually performed better than the new page. Okay, so it's not unambiguous, it's not perfectly unambiguous that the new page is better than the old page. Okay, so like this seems to be obvious, so like I don't want to hammer this home too much, but it speaks to a deeper underlying aspect of doing data science versus making kind of other forms of weaker decisions. Often in the real world, we need to talk about our confidence in a decision, and merely saying that the new page is better than the old page, full stop, is incomplete, and it's, just to be fair, a little bit dumb. We need to think a little bit about our own uncertainty about the statistics we're computing. Bootstrapping allows us to do that through these confidence intervals, and it allows us to compare any particular statistic, and in this case, no difference against that confidence interval. So indeed, if the new page just takes more energy, or it takes more resources, or it costs more to keep maintained, is a difference of 2% or 3% or 4% actually going to be meaningful to us, weighed against the cost of maintaining this new page? And again, the bigger picture, getting extra validation. Will this observation hold next month? Will it hold on mobile devices versus on the desktop? Will it hold in different regions if we sampled the big set of data somewhat differently? We need to think carefully about how we gathered the data in the first case. So some evaluation and quality checks. Before trusting this bootstrap-based conclusion, we need to ask, are the users in this A/B test representative of future traffic? Were these users truly randomly assigned to the old page versus the new page? Maybe in our big set of data, young users were sent to the old page, somewhat older users were sent to the new page, and any differences in the behavior of those users will manifest in the differences we observe. And it has nothing to do with the quality of the page, it has everything to do with the nature of the people assigned to those two different groups, the A group and the B group, the old page and the new page. Are the observations actually independent from one another? Is one user one row, or do you have multiple rows of the same user in some cases, and how does that affect your overall statistics, including the bootstrapping statistics? Are your observations stable if you change the bootstrapping seed? So if you're, we randomly sampled big B samples, but the sampling distribution could have an effect on overall computing statistics. If we changed the randomness, would that have changed our outcomes? There's all these things we have to dig deeper into. If we change the sampling window, would that have changed? So again, stability is important. There are various diagnostics you can run. So you can compare, you can do bootstrapping, you can take different time slices and you can compare the bootstrap confidence intervals over all of these different samples. So in some sense, you can take a bootstrap of a bootstrap and you can not only compute your averages of averages within confidence intervals once, but you can do that over and over again for different sets of the data, and you can compare the bootstrapping confidence intervals to each other. Are the intervals more or less always the same, or do they somewhat shift? If you do bootstrapping once and you get a 95 percentile way to the right, and you do it again and you get a confidence interval way to the left, this can maybe further degrade your certainty about the quality of your analysis. And hopefully it would, because you're a thoughtful, smart person. You check subgroups, you check mobile versus desktop, you maybe look into demographics, you look into fairness, as we've talked about, and maybe even you compute multiple metrics. So click-through rates, downstream retention, conversion, these are all going to be important. So don't just be superficial, be thoughtful and go deep. So just wrapping up a little bit, it's very easy to do this yourself, as you've seen from the code I've provided for you, but there are implementations in Python that can do some of this for you. In particular, SciPy has a stats sub collection in the library, and within that there's a function called bootstrap, and this will implement the generic bootstrap algorithm that you coded by hand. You can go ahead and click on this link and read more about it. You can, for bootstrap, in part of the SciPy library, you'd pass in your data and a statistic function like np-mean, and it will compute the bootstrap and the confidence interval using the statistic you provide. Just walking through this code quickly, here is where I import the bootstrap from the scipy.stats package. I'm also importing numpy, and I'm just going to call it np for the sake of efficiency. I'm taking my random number generation, I'm giving it the seed 1109, as I often do in this class. I get my normal distribution with a provided average and a provided standard deviation and a sampling of 50, and that gives me X. That's my overall data. And here's what I actually call bootstrap, which I just imported a moment ago. This uses the data X. This says use the function mean. My confidence interval is 95%. So again, this is going to go between the 97.5th percentile and the 2.5 percentile. If you provide a different confidence interval, this will change. This n resamples, according to the documentation of Bootstrap, is basically the size of big B, how many iterations of the bootstrapping I want to do. This says percentile, and this is the random number generation, which I've defined above. And then it'll give you the confidence interval, low and high itself. Again, this is just another implementation of what we did a few moments ago. It's not that much more efficient than just doing it yourself, but if you so choose, you can use this library for the task of bootstrapping. Scikit-learn, which is one of the libraries we use as a kind of a gateway to machine learning, also implements a bootstrap style resampling inside what we call ensemble methods, which we ought to see later on in the course when we talk about machine learning. But there's bagging classifiers, bagging regressors, random forest classifiers, and random forest regressors. These are all going to be machine learning models, but they use under the hood something like bootstrapping in order to compute statistics in a robust, meaningful way. So the core concepts of this module apply to these classifiers when you get to machine learning. It also provides this function sklearn.utils.resample that allows us to do general purpose resampling. And here it is. So you can look into it yourself. But given a data X and its labels Y, you can resample these with replacement. So again, you sample them once, you put them back, so you can potentially sample the same data points again and again. You provide a random state, a random initial seed for your random number generation, and everything is as you'd expect. Stats models is yet another package that you can use to compute bootstrapping, standard errors, confidence intervals, but quite frankly, SciPy and scikit-learn are much more popular libraries for data science and machine learning. So where can things go wrong? Again, if your data overrepresents certain groups, so we're we only took patients who come in during the night, or we only used our click-through, the worked example 2, we only sampled high-income users. The overall sample from which you're doing bootstrapping will be biased in one direction or the other. So the bootstrapping, even if it gives you a more correct or more meaningful range of expectations for where your statistics should lie, if the original data is biased, then bootstrapping will just learn or reproduce that bias. Bootstrapping doesn't hide individuals, so repeated resampling may reveal some rare cases. It might expose problems of privacy. Like, this is a bit of a stretch, so I don't think we'll need to get into it too long here. But if you're doing bootstrapping and then you're going to be sharing samples, or you're going to be including logs in your reports, then occasionally when you're doing bootstrapping, that is a way to kind of identify which samples are very rare. And then that can be used to re-identify individuals. So it's a way of breaking privacy. Again, this is not a class on the data science security specifically. That might be even a graduate level class. But you can use bootstrapping sometimes for nefarious purposes. So something to consider when you get to be more advanced. Fairness and equity. So considering average improvement, this might risk harm to subgroups. So merely considering averages might mean that we're ignoring that a particular demographic ends up having longer wait times. If all you're doing is aggregating things in the whole, this can ignore subtle differences in subgroups. And overconfidence. So you might get confidence intervals that are very narrow, right? So from 97.5 percentile to 2.5 percentile, those are very close to each other. So 95% of the data is in a very narrow range. If the data, again, you're acquiring is non-representative, this indicates that you're very confident about something, but it ignores the bigger picture, and it ignores the fact that this narrow confidence interval comes from a biased original sample. So again, the same old mitigations to these kinds of problems apply. You'd inspect and compare subgroups before and after any kind of changes or any kind of intervention you're doing, like we saw with the website. You'll have to document how the sample was collected, who might be missing, and try to expose any kind of biases that way. And then you'd combine bootstrap uncertainty with some domain knowledge. So once again, we'd have data scientists like us who are deeply knowledgeable and deeply thoughtful and have a wide variety of tools at our disposal. We'd produce reports, but they wouldn't be final. We'd discuss them necessarily with people who understand wait rooms or clinical contexts. So we'd work with doctors and nurses, or we'd work with maybe psychologists or people in marketing in the worked example 2 on websites. We'd work with people in different domains to interpret these results. So later on in Module 32, we'll see distributions. We'll see something called p-values, which I have the scary face on, but p-values is within the context of statistical significance. Again, allows us to make estimates about how confident we are about our computed models, our computed predictions, our computed expectations, and so on. So bootstrapping is sort of our first view into this world of computing statistics on our statistics, and using those statistics on statistics to describe our confidence about our uncertainty about our data. This is related to simulation-based hypothesis testing, so randomization tests, permutation tests. We might see Monte Carlo later on, which is a really fun example of doing sampling to compute a model for something. And again, we're getting slowly into machine learning. So bagging, I mentioned random forests a moment ago. Ensemble methods use under the hood a lot of the techniques from this module in order to get machine learning models that are far more robust and more performant than even more advanced models on paper, because they do this sort of resampling under the hood. We'll also talk a little bit about cross-validation a little bit later, which uses repeated splits of the data to more properly estimate performance. In practice, real resampling style ideas show up in model validation. We'll talk about this later. Uncertainty estimation, robustness checking, which again is going to be very important, especially in high-stakes contexts. And it reminds us of the key mindset we need to have as proper scientists and proper individuals, rather than just memorizing formulas, which nevertheless is important. we need to be able to think about the idea of testing and testing our hypotheses and not being satisfied with a particular set of results. We can ask the question, if I can simulate different samples, different observations, what would happen if I did that many times, right? Like, how confident am I in the statistics? Going back to the manager from the very beginning of this module, we described someone who says, well, our wait times are less than 35 minutes on average, but how much do we trust that average? Now, hopefully, you have a better idea that average falls within a measure of uncertainty, and we're going deeper and deeper into understanding statistics, and we're getting closer and closer to the truth, and we're not being satisfied with just high-level, superficial pablum. So please go to the slides and do the quick checks. Make sure you understand these concepts. And here's the references from today. It's a pleasure as usual. See you next time.